the last few lectures, we have learned how the combinational circuits can be designed using functional blocks or the fundamental circuits like decoder, multiplexer, adders, etc. Lastly, we have seen some generalized structure of realizing combinational circuits using multiplexer. Now, today we will read another type of combinational logic design using programmable arrays of logic gates. But before that, before we start that programmable arrays, quickly we solve the last day's quiz question. The question was that a design, it is a 4-bit barrel shifter using multiplexer. So, answer we see that already we have discussed the 4 to 1 multiplexer design. It has 2 select lines and 4 input lines, 1 output lines, and this is the IEEE symbol for 4 to 1 multiplexer. We will use this multiplexer to design a shifter, 4-bit shifter. Now, first we see the normal combinational logic shifter. See, this is 4 to 1 multiplexer we have used. This is my mux 1, mux 2, mux 3, mux 4, or reversely we can take that outputs are S1, S2, S3, S4, and the functions that F1, F2, F3, F4 that we want to implement or we want to pass that thing as the output. Now, there are the shifter has 4 different combinations it has, mainly these are my select lines. So, this is my S1, S0. Select lines, and this is my mode of operations. So, if the select lines are 0, 0, whatever we are applying in the F input, that is as it is passed to output, that means F is passed to S. When it is 0, 1, it is shift right, 1, 0 it is shift left, and 1, 1, then it is a reset type of operation, that means all zeros are passed to S. Now, we see how the circuit behaves like that. See that H1 H0 is 0, 0. If it is 0, 0, then this select line should be or this the first input line 0 should be passed as the output. Now, similarly for S3, this 0 line should be passed, here this should be passed, here this should be passed. So, whatever we are applying, that actually the first 0th, it is 0th input, and the F1 to F4 is attached with that. So, it will be S is F. Now, when H1 H0 is 0, 1, then if H1 H0 is 0, 1, then the first input that should be that one input should be passed to output. This should be the situation. Now, see here a input IR is fed to the first input. First input of S3 is, see this is the F4 this is my F4, this is the F4 line. Similarly, the F3 line, this is F3, see this is F3, that is fed to the first input of S2, and for 0 1 combination of H1 is 0 or S1 is 0, it is passed to S2, and the F2 is passed to as the S1. So, what is actually doing? It is F3, F4 is S3 is F4, S3 becomes F4, S2 becomes F3 and S1 becomes F2, and one S4 can be I4, or if it is periodically connected, then it can be F1. So, it is actually one right shift. So, if it is the select lines are 0 1, it is a right shift. Similarly, that now if it is 1 0, if it is 1 0, we see that actually for 1 0 the second input will be fed to, or it is passed as output, second input. Now, what is the second input? So, if it is select line is 1 0, then second input is, see it is F3 is passed to SO4. Similarly, F2 is passed as S3. F1 or F1 is passed as S2, and a input IL, or that just like the right shift, it can be F4 also, that can be fed to S1. So, what we achieve? That for H1 H0 values as 1 0, we get that S4 equal to F3, S3 equal to F2, S2 equal to F1, and S1 is some IL, or if it is periodically connected, then it can be F4. So, it is nothing but a left shift, everything is shifted left. Now, we see that for select line 1 1 combination, what will happen? For select line 1 1 combination, see that this fourth input, that will be passed as output. This is the situation. Now, in this particular design, the fourth input is stuck with 0, some 0 input. So, this is some 0 input. So, when it will be H1 is 0 is 1 1, then all S4 equal to 0, S3 is 0, S2 is 0, S1 is 0. So, this is some reset type of design. So, what we see that there are 4 combinations, and if the select lines, if my select lines are 0 0, as it is the inputs are passed to output, 0 1 it will be shift right the 4 bit, 1 0 then the 4 bits are shifted left, and then if it is 1 1 then it is a reset type of thing, the all outputs become 0. So, this is one design of the shift. Now, there are in real life practice, there are many other different type of shifter are possible. Actually, barrel shifter we uh, can design like that, or we can define that, say if there are 4 inputs and there are 4 output. Say these 4 inputs are I 0, I 1, I 2, I 3 and outputs are O 0, O 1, O 2, O 3. Then the problem can be stated like that, or this is my problem definition, that 4 bit barrel shifter, that see I 0, I 1, I 2, I 3 and say O 0, O 1, O 2, O 3. Now, say for one situation that there can be different type of shifts. Say I am defining shift type. If shift type is say 0 type of shift, means as it is the inputs will be passed to output. That means, if it is shift type 0, it defines that I 0 or O 0 is O 0 equal to I 0, O 1 is I 1, O 2 is I 2 and O 3 is I 3. So, this is one type of shift. Now, if it is, say I am taking shift type 1, shift type 1, that means it will be problem is like that, that say if it is I 1, I 2, I 3, I 4, O 1, O 2, O 3, then all the bits, input bits will be shifted by 1 bit. That means, this type of shifting is there, that either I 4 can go here or that can be fed as 0. So, it will be O 1 is either some, it is shifted by 1. So, we can tell that it can be IR or I 4 if it is periodically shifted. O 2 is I 2, O 3 is or O 2 is I 1, O 2 is I 1, O 3 is I 2, O 4 is I 3. So, this is one type of that is, if it is shift type 1, then it will be the, if it is shift type 2, if it is shift type 2, then this type of shifting is there, O 1, O 2, O 3, O 4 and there will be 2 shift. That means, I 1 will be shifted to O 3, I 2 will be shifted to O 4 and I 3 can be shifted to O 2 and I4 can be shifted to O1. There will be two shift, or I3 will be I1 is O3, I2 is O4, actually I3 should go to there will be two shift. So, I1 should be see that it will be 2 bit shifted. So, I1 comes to O3, I2 comes to O4, I2 should goes to O2 and I3 should goes to O1 and I4 should goes to O2. So, this type of combination I will get, that I1, I2, or if I write that O1, O2, O3, O4, then O3 will be I1, O4 or O3 is I1, O4 is I2, then O1 should be I3 and O2 should be I4. These can be different input also, but if it is periodically shifted, then this type of shiftings are we want. That means, now if we summarize, we want a 4 bit barrel shifter like that, that if it is I1, I2, I3, I4, O1, O2, O3, O4, then first type of shift will be that as it is, I1 will go to O1, I2 O2, I3 O3, I4 O4. Second type of shift will be I1 will go to O2, this is the one shift, and it will go to O1. Now, third type of shift will be I1 will go to O3, I2 will go to O4, I3 will go to O1, I4 will go to O2, and in that same way we can still do some more. Say if it is I1 can go to O4, I2 can go to O1, I3 can go to O2, I4 can go to O4, O3. So, this type of shifting we want, or if we just in color if we write that actually this shift type we can tell that shift type 0 means it is represented as a black, then shift 1 means it is represented as a red, shift 2 means it is represented as a blue, and shift 3 is green. So, this is one type of shifter we want to design. So, this will be the quiz of our the current lecture, that lecture 19, that again we have to design this type of barrel shifter, the 4-bit barrel shifter, where will if we select or if we want that shift 0, 1, 2, 3. Again we call this is our this is one type of barrel shifter. So, our lecture 19 quiz is again this is our lecture 19 quiz, that we want a design a 4-bit barrel shifter, where the shifts are just now we defined that shift 0, shift 1, shift 2 and shift 3. And shift 3. So, this is our next quiz. Okay, now we start our new lecture, that means that programmable logic arrays. Okay. First we define what do we mean by programmable arrays of logic gates. See that combinational logic circuits can be designed by using general AND and OR array structures. See what so far we have read that all combinational logic can be realized by a set of functions, where the functions are represented as the sum of product form. Now, this sum of product form means what? Sum means our OR gate and product means the AND gate. So, mainly it is a AND OR realization. Now, this AND OR realization, this AND from logic to logic or from one circuit to another circuit, this AND OR combination will differ. Now, the concept is that if we predefine some AND arrays and OR arrays, and depending on the circuit, given circuit or the circuit to be realized, if I select the AND, means the product term will vary, or means the min term will be varying. Now, if I select a particular OR, then my combination will also vary, that means my sum function will also vary. So, I am getting a variable sum and product terms. So, obviously, one particular design will realize a number of circuits, combination circuits, only one restriction is the total number of variables must be equal. So, to arrange and OR gates into two different planes called AND plane and OR plane, and the whole structure is called the programmable, because we can program, we can change the product terms as well as the sum terms. Now, the two planes can form programmable logic arrays or programmable array logic. We will see later what is PLA and what is PAL, but all are programmable arrays using AND planes and OR plane. Now, specific functions can be realized in sum of product form, and they can be programmed by using PLA or PAL. So, if we see the structure, see these are my AND planes. So, if there are, say there are n number of inputs. So, we know that if it is a n inputs, then there are min terms possible, or the product terms can be 2 to the power n, 2 to the power n such product terms. Now, as if these are all min terms and they are fed to the OR plane. So, among these what is the function of this OR plane? The OR plane will select some of the min terms from this 2 to the power n min terms, and it will OR that thing, or it will be taking the sum to give a output. That means, if my this is A0, A1 to An minus 1 up to this inputs, and outputs will be say F0, F1 up to say some Fm minus 1. So, that means m number of outputs will be there, n number of inputs and m number of outputs. Now, we see how this is a programmable arrays, mainly the AND arrays and OR arrays are there, overall structure. Now, how this programmable design or programmable arrays can be used to realize the combinational circuits. Now, we take one example. Say I have 3 inputs and 4 output functions. So, this is a combinational logic where the set of outputs are 4 outputs, means that inputs are only A, B, C, outputs are W, X, Y and Z. Now, say it is already using Carnot, given the problem that it is minimized. Now, the outputs are or output expressions are W equal to A plus B dash C dash, X is A C dash plus A B, Y is B dash C dash plus A B, Z is B dash C plus A. Now, how first we see or we find out that how many distinct min terms are there in this particular output. So, the distinct min terms see A, B dash C dash, A C dash, A B, C again B dash C dash is there. So, it is not distinct, AB is also there, B dash C. So, there are only 5 distinct output or distinct, not output, this is distinct mean terms. So, if I can realize this 5 distinct mean term, then I should get the output W x y z. Now, see that product terms, this is the product terms. So, product terms, that 5 product terms A B, B dash C, A C dash, B dash C dash and A. Now, we see that how they can be, or this is nothing but that AND. So, A B means A and B, B dash C means that B complement, this is B complement and C, 2 input AND gate. AC complement, AC dash means A and C complement. B dash C dash means B complement, C complement and A means only one literal A. So, if these are the mean terms available, then the first output W is A plus B dash C dash. So, I have to take that, if I mark these product terms as 1, 2, 3, 4 and 5, then the first output is actually A plus B dash C dash, means from here this will be W is 4 plus 5, this is 4 and 5 OR. See, so the output W, this is OR plane, this is my OR plane. So, output W is ORed and the 2 inputs are 4 and 5, means that B dash C dash, this is my B dash C dash and this is my A. Now, similarly, what will be my X? See, the second column is my X and X is AC dash plus AB. So, I will take that X is my 3 and AB is my 1. So, in the second column or in the column of X, that where the AB term is there, that means the first product term AB, there will be 1 1 and AC dash means 3. So, that means if 1 exists in the AND plane, that means I am taking that as the input of my AND gate, and if in a column in the OR plane a column consists of 1, then that particular product term will be the input of the OR gate. So, if we summarize, then what we can write, that for the AND plane, or we can tell AND array, this is a 2D array, that see that A, B, C, these are the, if one row that 1 1 in the column represents that the particular literal or variable is one of the input of AND gate, and the number of one in one row gives the number of variables as the inputs of AND gate, or actually it determines that the how many inputs of the AND gate is needed. That means, if say A, B, C in one row all are 1, that means it gives the term product term A, B, C, which is actually a 3 input AND gate. This is a 3 input A, B and C, 3 input AND gate. So, mainly the AND arrays, the left hand side the AND arrays they represents that how we can take the different AND combinations. Now, similarly, this is my OR plane. So, these are mainly the AND gates, these are my AND gates, this is the AND and these are my OR. That this sum of product forms. So, this product that will be taken from these variables, complemented as well as uncomplemented, and the outputs will be represented by this OR of these ANDed outputs. So, if one exists, similarly if one exists, then that particular, now it is only in the column. So, for AND it is in the, for OR plane that 1 in a column represents that the particular product term or we can tell mean term or we can tell the AND output is the input of one OR gate. And here the number of one in one column tells about the number of OR input. That means, say if I have one output line W and in this column there are, say there are two ones, that means I need a 2 input OR gate. So, this product term say is P1 and this product term is say P2. So, this is my P1, this is my P2, and P1 P2 is actually some AND output, because these are the say some AND gate output. So, this is the realization. Now, we see the structure, how this array structure has been done in real life. See, this is the, for this particular example, say ABC are the 3 inputs. Say this is A, say this is B and this is my C inputs. Now, as in the functions or the output expressions, the complement variable is also exist. So, first I realize that A bar, B bar, C bar by giving 3 inverter. So, these we can write as A bar, this is my B bar and this is my C bar line. So, this is A bar, B bar and C bar. So, these are my inputs. So, if it is a 3 variable or 3 inputs, but actually when it is implemented in real life, as if we are assuming that 6 inputs are available, 3 complemented variables and the 3 are uncomplemented one. Now, these are my, so and these A, B, C and A dash, B dash, C dash are fed accordingly as already we have seen in the example. So, this is my AND gate. So, there are, as there are 5 distinct product terms, we have seen that there are 5 distinct min terms, A, B dash, C dash, A C dash, A B, B dash C. So, these min terms are actually generated by this. See here, this is a AND gate. This is one AND gate. So, these 5 min terms, 5 distinct min terms, they will be available here. Now, and there are 4 outputs, where the 4 outputs are, the 4 outputs are W, X, Y, Z. First one is A plus B dash, C dash. So, W is okay. First we see the generalized thing, that this is my AND plane, and then we will discuss that part. So, this is my AND plane, this is my plane and this is my OR plane. So, why it is programmable? Because this is for 3 input, this is a structure for 3 input and 4 output programmable design. So, any 3 input variable product term or min terms I can get by using this 5 and then as all any min terms or any product terms are available, then any combination of or combination I can get from these all possible product terms and I can realize the any 4 output from this all possible 3 input product terms. So, this is a totally variable structure. That variable means that I can get any product terms from this 3 input variable, I can get any 4 output from here. But what we can do that if it is 5 output or 6 outputs, then I can add in the OR plane, I can add some more. I can add say F4, I can add F5 like that. Okay. Now, we see that what example we have discussed, it is more concrete. So, again if we draw that the ABC lines, say these are my, this is my A, this is my B and this is my C line. Okay. So, this is A, B, C. Now, first what is done that A complement, B complement and C complement, that also has been realized by using these inverters. These are the inverters. So, this is my A complement, B complement, C complement. Now, for this particular example, say what these AND gate, output of this AND gate, the first AND gate. See, it is taking B as one of the input and A bar or A and B. So, that means this is my AB. Similarly, what is this output? See, this is C and this is B bar. So, this is B bar C. This output is, this is C bar and this is A. So, this is my AC bar. This is that this one is B bar and this is C bar. So, this output is B bar C bar. This output is simple, only one, actually one input get. So, this is A. So, this is my AND plane and this AND plane they are generating these 5 distinct product terms that we actually need for to evaluate my output expression W x y z. Now, what was W? We remember that W was A plus B dash C dash. Similarly, x is A C dash plus A B. We see W is So, W is my A plus B dash C dash. So, if this is my W, it should be one input should be A and B dash C dash. Similarly, the X is AB plus AC dash. So, this is my X. Y is AB plus B dash C dash, and Z is the B dash C plus A plus B dash C dash. So, this is my OR plane. So, here this if I want to represent this as the matrix, then what I can do, that actually if one particular variable is the input of one AND gate, then I will put a 1 or say cross in that position, otherwise I will give a 0. So, now how many rows and columns it has? See, then in the AND plane the number of columns will be that twice that of input variable, and the number of rows will be the number of distinct minterms exist in that particular function that I want to realize. So, if now I can tell that design the AND plane. One is the number of rows will be the number of distinct minterms or product. And number of columns will be the twice as that of the number of input variables. Why it is twice? Because I need complemented as well as uncomplemented variables, input variables. So, for 5 variable input, say if a function has 5 variable function which is say 8 distinct product terms. Then the AND plane should be that number of columns are 10 that and there will be 8 rows So, now if I give the name, then say I am telling this is my A bar, B bar, C bar, D bar, E bar. These are my 10 variables, and that 8 distinct product terms it will generate, say that P1, P2, P3, P4, P5, P6, P7, and P8. So, these are my 8 product terms and these are my 10 input variables. So, this is the structure of my AND plane. Now, what will be the structure of the OR plane? Then OR plane, that product terms will be same, say that 8 product terms will be there, and say I have 4 output, then this 4 output will be the this column, say W x, Y, Z, these are my outputs, and this P1, P2, P3 to P8. Okay, we will finish this lecture here and we will continue in the next class. Thank you. Today we will continue the discussion that last day we are doing, mainly the logic design with programmable arrays. Now, today we will see that the logic design with PLS.